Before we proceed in proving the general form of Damobrot theorem, using the concept in the previous video on the product of two complex numbers, let's introduce the concept of the ratio of two different complex numbers. So we have here our z sub 1, which could be expressed in this manner, and z sub 2, which is also in this manner. Let's try to prove that the ratio of them, considering that we have these notations, is actually equal to the ratio of their modulus times this notation here. Okay, again, this is not necessarily the Damobrot theorem in itself, but we are going to prove this as well as a practice of the concept at the same time to deepen our understanding on the proof of the Damobrot theorem using the concept in the previous video and probably concepts to be discussed here as well. So for our proof, okay, we will have to accept this. I'm not going to write anymore let z sub 1 equal to that or z sub 2. Let's use the already identified or provided details here for z sub 1 and z sub 2, so we can just automatically proceed to the ratio of z sub 1 and z sub 2. Of course, if you're going to take the ratio of them, you're going to take the ratio of these two representations. So you have here r sub 1 and then times cosine theta sub 1 plus I sine theta sub 1. This corresponds to the first complex number to be divided by r sub 2 times cosine theta sub 2 plus I sine theta sub 2. Okay? So with this now, since r sub 1 and r sub 2 are both scalar quantities, so if we're going to take them out, we just have here already the expression for r sub 1 and you have here r sub 2, which actually fits the first portion here. So our task is to only to show this later on from the result of this. Give her cosine theta sub 1 plus I theta sub sine theta sub 1 over cosine theta sub 2 plus I sine theta sub 2. This is sub 1, sorry. This should be 1 here. Okay, so we are going to manipulate this portion here and hopefully we could arrive into this form using the sum and difference identities. Now what would I need to do here is this. Of course, I'm going to write the same ratio of r sub 1 and r sub 2. Allow me to multiply the same expression here in the denominator. Okay, so that I can actually look for another equivalence of an identity and notice what will happen later on if I'm going to do that. So if I'm going to have here cosine theta sub 1 plus I sine theta sub 1 over cosine theta sub 2 plus I sine theta sub 2. Again, I'm going to multiply the denominator with the same cosine theta sub 2 plus I, I'm going to multiply with, let's say, negative. I'm going to multiply with the conjugate. Sorry, not the same, similar. I'm going to multiply it with the conjugate. Okay, theta sub 2. And take note, since I'm going to multiply the denominator to retain equality, so this is just equal to 1, right? So I'm just multiplying 1 to the entire expression, but of different expression. So what will happen here is this. So we still have here r sub 1 over r sub 2. What will happen for denominator and numerator is cosine theta sub 1 plus I sine theta sub 1 times this numerator cosine theta sub 2 minus I sine theta sub 2. Our denominator would have cosine theta sub 2 plus I sine theta sub 2 times cosine theta sub 2 minus I sine theta sub 2. Okay, I did not multiply them in the meantime. I'm going to do it step by step. So for the third one, this is where I'm going to multiply. For the numerator, allow me to do this using what they call this one, FOIL method. This term and that. So we would be expecting cosine theta sub 1 times cosine theta sub 2, right? For the inner terms, we have this and that. Sorry, I'm going to change the color here. This one, inner. So you will have here plus I sine theta sub 1 cosine theta sub 2. Outer minus I. Take out, it should be minus I cosine theta sub 1 sine theta sub 2. And finally, you will have the form, the last terms. So negative times positive would be negative I squared sine theta sub 1 sine theta sub 2. Okay? That's for the entire numerator. For denominator, take note I'm multiplying conjugates. Don't forget that if I'm going to multiply conjugates, just like in quadratic expressions, in radical expressions, even here, I'm going to multiply conjugates. We're just simply going to use the difference of two squares. Take the square of the first term. You have here minus, take the square of the second term. So you have here I sine theta sub 2 square. Okay? That would be the entire expression here. I might be using another page if this would not be fit here. So for our numerator, allow me to rearrange them just like what I did in the previous video. Allow me to use this one here, this one, okay? This one here as my second term. But take note, it's minus I squared. I squared is actually negative 1. So minus negative 1 would be plus 1. Again, because minus I squared is already, what do you call this one? It's minus, and then I squared is negative 1. So I'm going to, if my task is to make this as my second term, what will happen now is that it will become plus 1. Okay? So I'm going to place it here as my second term. That would be plus sine theta sub 1 sine theta sub 2. And then for the remaining two terms on my numerator, I'm talking about this. Okay? I'm going to factor out I, positive I. Okay? So what will happen here is I'm going to take out positive I, so plus I. So the first term is sine theta sub 1 cosine theta sub 2. This will still be minus because I'm just trying to factor out I from this one here. So you'll have cosine theta sub 1 sine theta sub 2. Okay? That's for the numerator. Okay? The reason why I'm doing that is because I have to come up with this grouping to come up with the identities in sum and difference formulas for trigonometric functions. In my denominator would just be cosine squared theta sub 2. You have here minus. In the meantime, it's just minus I squared sine squared theta sub 2. Okay? Probably you are already thinking of another step here, but allow me to combine this one here. So for my numerator, I'm going to do it like this. Okay? This is actually one of the identities that we can use here. We have cosine first angle times cosine of the second angle plus sine of the first angle and sine of the second angle. That we can use there the cosine identity. But if it's plus, it will be difference formula for cosine. It's the other way around. It's actually equivalent to the cosine of the difference of theta sub 1 and theta sub 2. Again, for cosine, the sum and difference formulas, if this is plus and it follows cosine, cosine, sine, and sine of different angles only, so we will have here minus, that is opposite. But the second one, on our numerator still, plus I, if you have here sine, cosine of the first and second angle, and similar here, first and second angle, but cosine and sine, and minus now, we're going to use here the difference formula for our sine. So if it's minus, for sine, it's still minus here. So you have sine, or let me remove the grouping symbol because automatically it means multiplication, sine, the difference as well. Take note for cosine, opposite signs. For sum and difference formulas, for sine, similar for signs. Okay? And my denominator will be like this. We have here cosine squared theta sub 2. And again, take note, just like what happened here earlier, your I squared is negative 1. So if you have minus I squared, so minus negative 1, you have plus sine squared theta sub 2. Take note of the identity at the denominator. It's actually cosine squared plus sine squared of the same angle here. And what does this tell us? If we're going to have cosine squared of x plus sine squared of x, it's just equal to 1. So the entire denominator is just equal to 1 in itself. So finally, we can have here r sub 1, r sub 2. Our numerator is cosine theta sub 1 minus theta sub 2 plus I sine theta sub 1 minus theta sub 2. Okay, all over 1, which is this is actually equal to 1. Or basically, you don't need to write 1. And this is actually the proof that the ratio of two complex numbers is equivalent to the ratio of their modulus and the sum of the difference formulas for cosine and sine with together with an I for imaginary part. That's actually what we're trying to show here. Okay, the difference for cosine plus I, difference formula for our sine, and the ratio of R sub 1 and R sub 2. So we're able to capture that as proof here. So hopefully you're able to appreciate again the sum and difference formulas in trigonometric ratios. This might not be the De Moivre theorem in itself, but we're going to use some concepts here together with the previous video on the product of two complex numbers as we show the proof of the De Moivre theorem, which talks about the nth power of a certain complex number. Thank you very much for watching.